So let me quickly go back to this case K. G. So G is a finite P group. Characteristic of K is P, and then we had M, and I think, so now I try the following. I think the square of the order of G does it. So by induction, with respect to the order of G, so then we can, so if Z is the center, then I can look at KG, at the kernel of the projection to G mod the center. Right, and then I know by the induction hypothesis, I know that M to the order of G by Z squared lies in here. And on the other hand, this kernel is generated by all H minus 1, H runs through the center, and now they are central. So here this stupid mistake does not hold, so I have H minus 1 to the order of the center, right, is H is 0. So these elements are all killed by the generators are all killed by the, and now this, because they are central, right, I mean, so if I take, so it follows that the kernel, this kernel to the square of the center is 0, because now if I take, I mean, so I have that many, a product of these generators with that many factors, and they are central, so I can order them accordingly, and I get at least one which occurs order Z times often, and so it's 0. Okay, and then in the other proposition, we are still left with the, right, I mean, this was the proposition, still the characteristic of K is P, and G now is pro P. And we do know already that that then lambda G is local, and the maximal ideal is the Jacobson radical is J of G. And we also know already that the J-adic topology, JG-adic topology, is finer than the pseudo-compact one. But we claim, so the remaining claim is that they are equal, these topologies. So we do know that already from proposition, I think that was, right, I mean the other assumption was, I should repeat, G is topologically generated by finitely many elements, which were called, which let me call them G1 up to GR. And then we do know already from proposition 152I that this ideal then is generated, I mean, as left or right ideal, as left or right ideal by pi, and then these elements Gi minus 1. So this means, so it follows that all the powers jg to the I all are finally generated. I mean, I don't need, of course we could write explicitly down generators, but I don't think I need this finally generated as, say, left ideal. So, as such, being finally generated, they are closed. They are closed in lambda g. I mean, this is again a general principle. I mean, in the compact case, right, it would be clear they are the, I can write them as the image of a finally generated free module into lambda g. And so if lambda g would be compact, this is because, I mean, any map from a finally generated free module is continuous, and if the ring is compact, the image would be compact. And the same holds somehow for pseudo-compact. The image is pseudo-compact and therefore closed. This is one thing, and the other thing is also because it's finally generated, each step is a finally generated over the residue field, right? Over lambda g mod g, which is k. And so this means, so this implies that lambda g modulo jg to the I is a lambda g module of finite length. And you see, on the other hand, it is because they are closed, this is closed, the quotient is again and a pseudo-compact module. But again, I mean, this is a thing which would be clear in the compact case, right? That then this thing is the topology has to be the discrete one, and the same holds in the pseudo-compact case. So, right? I mean, in the pseudo-compact case, it's still Hausdorff, and I would, but I cannot have infinitely decreasing sequences of submodules. So somehow. The trivial submodule has to be open, so it follows is discrete, topology is discrete. Follows they are open. Okay, so therefore in this case the topology is the jg-adic topology. Now let me mention, just for, I mean, in principle, I think later we do not have to use that, because we will always know much earlier, already from a much earlier stage on, that the groups we are looking at will be topologically finally generated. But later we will also prove that these rings for the groups we are interested in are Noetherian, and so I think I should mention this general principle. Suppose I know that the ring lambda g is, I mean, this is a fact about, I formulated only for lambda g, but it's a general fact about pseudo-compact rings. If I know that a pseudo-compact ring is Noetherian, then its topology is the Jacobson-adic one. And then in some sense one doesn't have to worry anymore about the topology, and any left or right ideal is closed. I mean, this is of course then clear because it's finally generated, and in general, as I said, in a pseudo-compact module, any finally generated submodule is closed. So the statement which is not obvious is this one. But I mean, I won't prove it. I just want to inform you. I think it's interesting to know, to have this in mind. Okay. So now I want to discuss, although this is for the number theorists among you will be boring, but since actually I later on, this is not only an example, later on I will make use of it in a crucial way. I want to discuss the commutative case, so the example of the group. So I take the additive group of p-adic integers to some power. So this is my group now. So now G. So, and we will compare this with the formal power series ring. Over O in D variables, x1 up to xt. And I denote right, I mean the maximal idea, this is a local ring, is local ring with maximal idea to denote simply by M, which is generated by pi and the variables. And so I can make it, I view it viewed as a pseudo-compact ring with respect to the m-adic topology. Right? Obviously, this ring modulo the powers of the maximal ideal are finite length modules, so it's pseudo-compact. On the other hand, let me denote by so GI in the group, in this group, I have so to speak the standard generator. So GI is right, I mean the element which has a 1 on the ith place, the standard topological generators dp to the d. Okay, and then we have the following proposition. Again, we suppose that the characteristic of the residue field is P, this P. There is a unique topological isomorphism of pseudo-compact O algebras from this power series ring to the completed group algebra of our group, which sending the variable xi to the element gi minus 1. Okay, so let me prove this. So we have, of course, on the polynomial ring, I mean, let me call this F0 from the polynomial ring. To here, right? I mean, we of course we have this map xi identity on the coefficients, and xi goes to gi minus 1. Now, I mean, remember that we do know from this previous proposition that, so recall topology on the completed group ring is the maximal adic one. And this idea is generated by pi and g1 minus 1 up to d minus 1. So it's completely parallel to this here. And this shows, right? I mean, this shows that that F0 is continuous for the, I mean, let me just say for the, okay, in one case I should take M intersected with the polynomial ring. And apologies. So F0 extends to an F as in the assertion. So we have the map, and we have to show that it is an isomorphism. And I mean, so let me write down two. I mean, the first set of equations is trivial. Clearly, if I take the formal power series ring divided by pi, I get the formal power series ring over K. And moreover, the formal power series ring is the projective limit of the O modulo pi to the M. So this is trivial, but the corresponding statements for the completed group ring hold as well, and they are, if you think about it for a moment, they are not entirely trivial there. So we also have that lambda p to the d modulo pi is the completed group ring over K. And this is the projective limit M of, I think I only need this one form, yeah. Exactly another this form. So, for example, here this projective limit, this is, you really need, this is not obvious. You need another fact about pseudo-compact modules. Right? I don't think that this is formally follows for any formal reason. It really uses the general fact. If you have a pseudo-compact module and you have in there, you have a system of closed submodules which intersect to 0, then the full module is always the projective limit of full module modulo these submodules. This is not, this is a theorem. It's not a formal thing, right? It's something which one has to prove. So whereas this set is trivial because of this concrete description of these rings, this is rests on properties of pseudo-compact modules. But you see from this that we need to show only so need to show, right? Need to show the bijectivity. Need to show the bijectivity of F. Then it's automatically, right? This I'm sure you believe immediately. If the things were compact, then bijective is enough for topological isomorphism, and the same principle holds in the pseudo-compact setting. So we need only to show bijectivity, and because of this observation, reduces us to doing this modulo pi to the m. We need to show that the maps are bijective. The map is bijective modulo each pi to the m. But then both sides are O torsion free. The power series ring is visibly, and the completed group ring, is the projective limit of free O modules, finally generated free O modules, so it's also O torsion free. And therefore, by induction, with respect to M, further suffices to consider F mod pi. So we are in the situation that we have K to K of Cp to the D modulo pi to the sorry. Okay, let me write it out. But you see, this is now we are using so this is the projective limit of K Cp to the D modulo P to the N, let's say. I use a different. Yeah, and this is the projective limit of K polynomials or power series, whatever, modulo x1 p to the n up to xt p to the n. And then, I mean, we only need to observe that in here, so in here, right, we have, for our standard generators, we have that gi p to the n minus 1, this is 1, minus 1 is 0, but now we are over k, so this is gi minus 1 outside p to the n. So this means that our map F actually is a map of these projective systems. Each step is mapped into the corresponding step here, and there it's completely obvious that it's a bijection, because I mean this is the product of cyclic groups of order p to the n, and in a single cyclic group I have, this is the only relation I have. So I mean this is what I have to divide out on the other side to get it. So bijectivity clear in each step. Okay.
What's wrong with using the universal property of CP to get a map in the other direction?
Yeah, I guess. I mean, I would have to. You see, I would. This is of course possible, but it's not without work. I mean, I have to give a map from Cp to the d into this ring. So I have to discuss that I can raise xi, that I can raise somehow this to p-adic powers, right? I mean, what is the map? So of course I could do this, but I would have to. I mean, it's not automatic. I would have to discuss also something.
I think after it's got and the generator to 1 plus xi.
Yeah, but you have to show that you can raise this 1 plus xi to a p-adic power. I mean, whatever. You can do whatever you like, but you have, I mean, you have to do something. I mean, it's not... so now let me mention...
I'm sorry, just one
Yes?
more question about your
Sure.
second inverse limit over there. So I just wanted to make sure I understood. Was your comment that to see that we need this fact that you just proved, that the topology is this J-adic topology? Is that what you were saying?
You mean here?
Yeah, the second inverse. You were saying that it's not a formality.
Yeah. No, this has nothing to do with J-adic topologies.
I was trying to see why it's not a formality.
No, I mean, how would you...
Well, the left hand.
I mean, maybe in this particular case, it is... maybe it's easier. One doesn't use the full abstract principle. I mean, we would know that these... I mean, how would you prove the surjectivity of this map?
The left-hand side is complete with respect to the powers of phi to the n, right? Because that's why I was saying, because you proved...
No, but that is actually is the question. I mean, is that true?
But you proved that the J-adic topology is the same as the original topology. So,
Yeah.
And so it's complete with respect to the powers of J, and phi lies inside J, right?
Yes.
So doesn't that give you the surjectivity? Powers of
I mean, the powers of pi is a much finer topology, right? If something is if complete for one topology, it's not necessarily complete for a finer topology, is it?
Okay,
But probably here...
I see what you mean. Okay, yeah, I see what you're saying.
Yeah. Okay, so now let me mention, although this is I'm not sure that this is later used in any crucial way. Still, I think it's something that should know about these completed group rings. So there is so far this was all a completely algebraic approach, together with some topology, but there is a functional analytic interpretation of the completed group ring. So G, again, arbitrary profinite. And let's say C infinity G is all locally constant functions from G to O, and C of G is all continuous functions from G to O. So now let's first look at the finite case. So if G is finite, right, then we have this pairing, then the usual group ring can be viewed as the dual of, there is no difference now between locally constant and continuous. Let me write C to O.
O is as before, yes. Yeah,
O is always through the whole course is this complete discrete valuation ring with some additional, this I won't repeat all the time. If I make additional assumptions on it, then I say it. Otherwise, there is no assumption. Right? Sending G, C to evaluation in G. That's an isomorphism. And so in general, right, if I have now my lambda G, then this is the projective limit of these finite quotients. And I don't repeat this, for each finite quotient I can replace it by this here, so Hom C G by N into O. And now I have the projective limit outside. So I can pull it in. I can pull it in. This is the same as Hom O inductive limit O the N O. And now, of course, the inductive limit here is just a locally constant function, so G. So I have this identification, which is, of course, pretty trivial. So we want to extend this a little. So always equip CG, the continuous functions, with the p-adic topology. Right? Then we have maybe not then. Independently, we have C of G is the projective limit. A function into O I can view somehow as the projective system of induced functions in the O modulo pi to the m. So it's the projective limit of the functions G to O modulo pi to the MO. But this I also can see as CG modulo pi to the M CG, right? I mean, certainly a function in here gets becomes the zero function here after projection to modulo pi to the M. And on the other hand, if I have a continuous functions where all the values are divisible by pi to the M, then of course the whole function is divisible by pi to the M. So on the other hand, these functions are automatically locally constant. Yeah? The map from C infinity to here is surjective. So this means, so follows that C infinity G is dense in C of G for the p-adic topology. On the other hand, any linear map, any O linear map is continuous for p-adic topologies. And this shows then that we have the following lemma, maybe only. We have lambda G, so which we view as a linear form on C infinity G with values in O. It's automatically, by this remark, automatically continuous for the p-adic. I mean, maybe I don't write this down. Yeah, the p-adic, but one has to worry about such things. The p-adic topology on here induces the p-adic topology on the submodule, on this submodule. This is in general not true, right, for abstract modules, so one has to worry about it. And so it's automatically continuous for the p-adic topology. On here, this is complete p-adically, so it extends by the density to CG. So we do get from O CG into O. And I don't have to mention any continuity condition because it's p-adic topology, so it's automatically continuous. Still an algebraic identity, although I have here this module of continuous functions. So lambda G should be viewed as the continuous O-valued distributions on G. Okay. So in the notes there will be here now then in this concludes the preliminaries, except that as I said already in the manuscript there will be a fourth section somehow collecting without proofs, collecting all the statements of about the notion pseudo-compact which was used. Okay, so now I hope that things will start to get a little more interesting.
This lambda G should be viewed as
The O module, if you want, the O module of.
Yes. So that was my question. It's function. It's an O module.
Yeah. I mean, there's I don't go into this, but also on the purely functional analytic side of distributions, you can define the product, the convolution of two such linear forms. And this corresponds to the ring structure of lambda. So distributions by themselves have a ring structure, and so this is actually an identification of rings, but since we don't use this, I don't go into it. Okay, so now part 2. So now I fix once and for all a prime number p. I mean, the title of this here is p-valued Pro p groups. Okay, so we now we will set up the basic axiomatics in Lazare is the notion of a. I mean, he does this all in much greater generality, which is part of the problem to read this. And of course, it's my task, I think, to strip it off.
So what was section 4?
Section 4 was the thing on pseudo-compact rings. So, one of the basic inventions of Lazare is this notion of a p-valuation. And actually, there is no point in setting this up for pro-finite groups. So let's for this section, actually let G be any abstract group. So for a while we work with abstract groups now. At a later point we will return to the case of a pro-finite group. Okay, a p-valuation omega on G is a function I should actually write the axioms then on the is a function omega G minus 1 to the open interval 0 infinity, such that and I mean with the, let me say this in parentheses with the convention so that I can formulate the axioms a little bit more uniformly with the convention that you extend this to 1 by omega of 1 is infinity. Okay, and that to keep them, to be able to keep them, let me write down the axioms here. So 4 axioms. First of all, the values are actually always strictly bigger than 1 over p minus 1. Then omega G minus 1h is at least the minimum omega G, omega h. C, omega of a commutator is at least the sum of the individual omegas, where here you have to be precise because Lazare does it in this paper differently. In other papers of his, he does it the same way. So in order to avoid confusion, so for me, commutator GH is GH G inverse H inverse. And finally, omega of g to the p is omega g sub plus 1. So raising an element to the p's power adds 1 to the p valuation. Now, I think, I mean, the axioms B, C, and D, they are kind of self-explanatory. I mean, the B and C are extremely natural. This, of course, is a serious, is still, right, a very natural-looking axiom, although it is a serious requirement. I mean, much more serious, as you will see, than the other ones. But A, of course, is kind of a mysterious axiom. If one sees it at first, I mean, one surely should wonder, what does it mean? I mean, the reason that I could have written this, of course, put in here, but I wanted to somehow to stress the fact that this is a particular axiom which I will not, cannot explain now. I mean, you will see later, I will point this out at places where this will be used in a crucial way. So I really wanted to list it as an explicit axiom and not put it here into the description of the function. Maybe one thing one can say already now, although you don't, probably you won't see any connection in the moment, is that this has to do with the radius of convergence of the exponential function. So this is in some sense, you will see this at various places, that this is one of the deeper reasons why for this requirement. Okay, so now let's derive a few other identities. So B for h equal to 1 gives that omega g inverse is bigger or equal to omega of g, right? And then by symmetry, omega g inverse is equal to omega g. So then B and C follows that omega, if we conjugate h by g, then this is omega of the commutator multiplied by h. So this is now I can apply, first I can apply B. This is bigger or equal to the minimum omega of the commutator and omega of h. And now we can apply C to the first minimum omega g plus omega of h, omega of h, which of course is omega of h. So I will not, so for quite a while, I will not make use of axiom A. I will only use here, for example, we only have to use that it's positive, the value is positive, yeah? So this we will use very often implicitly, that the value, maybe even here we don't need that it's strictly positive, but we probably will use at certain points that it's strictly positive. I won't mention this. I mean, when I will use the axiom A in the first time, seriously, I mean, really in the form it stands there, I will point this out. So for the moment, you can somehow be assured that I will not use it at all. So then again, by symmetry, right, we have equality. Conjugation preserves the function omega. And then, I mean, of course, the usual trick, maybe I don't do it, gives, if the, I mean, because it only rests exclusively on B, it's the usual trick with the strict triangle inequality. If omega g is different from omega h, then one has that omega G inverse H, inverse or not, doesn't matter, is equal to the minimum. Okay. So now let us, so for any real number nu, positive, strictly positive number, we define G nu is all G and G, such that omega of G is bigger or equal to nu, and we define G nu plus as all G and G so that omega of G is strictly bigger than nu. And so these are then by these are right, I mean by B they are subgroups, and by this here they are normal subgroups. So these are normal subgroups in G. So let me important simple remark, but because it's kind of important, let me really give it its own number. So G nu modulo G nu plus for any nu is a central subgroup of G modulo G nu plus. So let's take any two elements, I mean G and H, I formulate it this way, arbitrary elements, then, right, I mean C implies that the commutator, so this expression here, is strict. So now I use that the values are strictly bigger than 0. Is strictly bigger than one of them, so omega H, let's say. And so this means, of course, that this element G inverse H inverse lies in G. For nu I take omega H plus, right? And so I do get, by bringing this on the other side and using that this is a normal subgroup, I get that GH G nu H plus is equal to HG G nu H plus. And you see in this identity there is no requirement on G, but of course there is one on H. I mean the H has to be such that abstractly the nu of H, omega of it is the nu. So it has to lie in G nu. Okay, so this is simple but rather important fact. Now these right, these G nu form a decreasing exhaustive, I mean G, the union is everything obviously, and the intersection and separated, the intersection is just the element 1, so separated filtration of G, and two additional properties. One is, I mean, G in U is the intersection of all the G in U prime for U prime less than U. I mean, this is, I mean, both are trivial, of course, and the other is by the axiom C, if I take the commutator of group G in U prime. So by this, by convention, I mean in the following, if this occurs, I need this, even if these are only sets, I mean the subgroup generated by the commutators is contained in G U plus U prime. Right, I mean this is all totally obvious from what was written before. And so actually I can give it now. There is a unique Hausdorff topological group structure on G, for which the G in U form a fundamental system of open neighborhoods of the unit element. So this we will call, it will be called the topology defined by omega. Okay. So now let me spend the last 5 minutes by starting to discuss an example. So let's take any finite extension E of QP. And the usual notation is always the ring of integers. Pi E is a prime element. And V its additive valuation. I mean, I will later on, V is the standard notation for the p-adic valuation, and I use the same letter because, and this is important in the example, normalized by, so it is the extension of the p-adic valuation. So normalized by V of P is 1, not V of pi E. So fix a natural number n, and then we look at the algebra of n cross n matrices over E. And on this we introduce, so for such a matrix Aij, define W of A to be the minimum of the V of the entries, matrix entries, the valuations of the matrix entries. And if they are all 0, then this is infinity, of course. So, properties.
So if
Yes?
A has any elements there, it's infinite.
No. If it's a zero matrix, if it's not a zero matrix, it's just some rational number. But if it's the zero matrix, then it's infinity. Right? I mean, if I have a non-zero entry, then there is one of these values is finite. So the minimum
agree.
is finite. Yeah. So, I mean, this W of the sum is, of course, big or equal the minimum of the W of A and W of B. It's totally trivial because it's individually satisfied for V and each entry. Now, for multiplication, we have a little bit similar as over there. We have, I should say because I use it. So let me first say that again, always by the same trivial trick. We have equality if they are different. Three W of a product is big or equal to the sum. Right? I mean, if you compute the product of two matrices, the new entries are sums of products of old entries, and therefore the sum of you have an entry of A and you always have an entry of B in the product, and so the product V of the product is then in this case even equal to the sum, but because of the minimum you get in general only big or equal. And then also something we have to use for this example is if the VA is 0 for any A in GLN over the ring of integers. I mean, clearly, right? I mean, if the matrix has, all the entries of the matrix are integral, then V of A is non-negative. But if they are integral and it's invertible over the integers, then at least one entry has to be a unit, and so the minimum is 0. Okay, and now make the following definition. I guess I have to stop then with that. So now that I define G to be all G now, because of, I'm thinking, I mean, this will be a group, so I don't use A in this case, but G's, but it's all matrices in GL and E, such that W of G minus 1 is strictly bigger than 1 over P minus 1. And of course, omega of G is defined to be W of G minus 1. And so I have to stop here. So next time I want to do, although this is totally elementary, I still want to go through the computations that this omega is a p-valuation, that this G is a group and omega is a p-valuation. I mean, we see the first axiom by definition. I want to go through these elementary computations because in some sense they will occur over and over again, and so at least once I think it's useful to see them in order to get used to this kind of computing. Okay, thank you.